So in this video, we are going to talk about the trajectory of a projectile and the equation of motion attached to it. So trajectory of projectile, and the principle that we are going to be using is the Hamilton's principle. So looking at the problem statement mathematically, say we have an object that is undergoing a projectile motion, then it could have followed any path, right? It could have followed any path it wants. For example, it could have gone this way. Let's say this curve is some y of x, or it could have gone this way. Let's say this is some eta of x. Notice that eta of x is just a perturbation introduced to the original curve y of x, right? So we can write a new function, say y bar of x, which is equal to the original function y of x plus some epsilon times eta of x. Now small variations in the epsilon actually introduces perturbations to the original curve, which is very evident from this equation. And also the thing to note is that as epsilon tends to 0, notice that y bar of x actually tends to y. Now this is a very important thing that we are actually going to use later on in the video. So if we claim that y of x is the actual optimal path along which the projectile evolves, then y of x must be a stationary point, right? And I should write this down, that if say y of x is the optimal path, then y of x is equal to stationary point. It is a very important statement. It is a stationary point. Now, what does this mean? It means that if we construct a functional, say j, that depends upon y, and it could be written as an integral from x1 to x2, say f that depends on some x, some y bar of x, and some y bar prime of x dx, then if we take the first derivative of this functional with respect to epsilon at epsilon is equal to 0, then its first derivative must vanish. This is a very important condition, and this is actually very similar to the problems, to the simpler problems of maxima and minima, where we used to have one function and we used to differentiate the function with respect to x and equate it to 0 in order to find the extremum points associated with the function. It is very similar to that problem, right? So now doing this, substituting this in our first equation, it would give us a d by d epsilon of the integral from x1 to x2 of f x y bar of x and y bar prime of x, all being calculated at epsilon is equal to 0 dx, right? And by calculus of variations, we know the solution to such an integral. The solution is the Euler-Lagrange equation, right? So I should write down the Euler-Lagrange equation. It is it should be the total derivative d by dx of del f by del y prime minus del f by del y is equal to 0, and it should be equated to 0, so this is the Euler-Lagrange equation, right? And this equation is actually going to give us the equations of motion for our projectile problem. So now getting back to the physical problem, say we have a projectile. say we have a projectile that is following some path y of x, which we consider to be the optimal path along which the projectile evolves, and we have some other path eta of x. Then it is very clear that if y of x is the original is the optimal path, then the variation of the action integral from t1 to t2 of a function L that depends on qi, its derivative and time, must be equal to 0. Now this is the Hamilton's principle. This is known as the Hamilton's principle. Now notice that L is a function and is known as the Lagrangian, which is defined as the kinetic energy minus the potential energy. T is the kinetic energy and U is the potential energy. So the solution to this integral that we are looking over here, the solution to this integral would just be the Euler-Lagrange equation, which we could write in this form: d by dt of del L by say del qi dot minus some del L by del qi is equal to 0, where qi is the generalized coordinate, right? I should write this down. Qi is the generalized coordinate. Okay. Now let us get into constructing the Lagrangian for such a projectile. So now if we have a projectile, say that has been projected with a velocity u with an angle theta with the x-axis, this is the x-axis, this is the y-axis, then this projectile will have two velocity components, one in the y direction, which is just going to be uy is equal to u sine theta, and one in the x direction, which is going to be ux is equal to u cos theta, right? So clearly this projectile has 2 degrees of freedom, right? I should write this down. Degrees of freedom is 2, one along the x-axis and one along the y-axis. So if we construct the Lagrangian now, the Lagrangian is just going to be the kinetic energy minus the potential energy, which is going to be half mv square minus mgy. Now v can be divided into 2 parts, vx and vy. So we're gonna have half m x dot square plus y dot square minus mgy, where first let me just box this thing out, where it should be mentioned that x dot is dx by dt and y dot is dy by dt. This is just ux and this is uy. So we have the Lagrangian. All we have to do is put this Lagrangian in the Euler-Lagrange equation and get our equations of motion. But notice, since our projectile has 2 degrees of freedom, therefore we'll have to solve 2 different Euler-Lagrange equations in order to get the equations of motion, right? So the first Euler-Lagrange equation is going to be d by dt of del L by del x dot minus del L by del x is equal to 0. If we calculate this, notice that we do not have a x term in the Lagrangian. We have got an x dot term. We do not have an x term in the Lagrangian. So this term is essentially going to be 0. And for the x dot term over here, we are actually going to get mx double dot is equal to 0, which is equivalent to saying that x double dot is equal to 0, or d square x by dt square is equal to 0. Okay, so now this is a fairly simple differential equation to solve. We just have to integrate it 2 times and we'll get back the solution. So integrating it first time, we are going to get dx by dt is equal to some constant c, but dx by dt is nothing but x dot, and it is equal to the velocity in the x direction, right? So it is equal to ux, which is equal to u cos theta. So essentially what we got is that c is equal to u cos theta. We're gonna box it out. Now differentiating it a second time, we get x is equal to some ct plus a. A is some second constant. Applying our boundary conditions, we get that at t is equal to 0, x is equal to 0, right? This implies a is equal to 0. And so the solution is x is equal to ct is equal to u cos theta t. This is the solution to our first Lagrangian equation. Sorry, first Euler-Lagrangian equation, yes. The second Euler-Lagrange equation is going to be d by dt of dl by dy dot minus dl by dy is equal to 0. Now remember what our Lagrangian was. Our Lagrangian was just half m of x dot square, half m times x dot square plus y dot square minus mgy. In the Lagrangian, we have a y term and we have a y dot term. So let us first calculate the derivative with respect to y. This is just going to be minus mg. Now let us calculate this derivative dl by dy dot. This is just, this term would vanish. This is just going to be my double dot. So the equation of motion is going to be my double dot plus mg is equal to 0. This implies y double dot is equal to minus g, or it could be equally written as d square y by dt square is equal to minus g. So integrating this differential equation first time, we would get dy by dt is equal to minus gt plus some constant b. And notice that dy by dt is nothing but uy. So we can write that u sine theta is equal to minus gt plus b. Right, we're gonna just box it out. Notice with this equation that at t is equal to 0, the derivative of y with respect to t is just going to be, we put t equals to 0, so it is just going to be b, right, which is uy is equal to u sine theta. So we get dy by dt is equal to minus gt plus u sine theta, right? Now integrating it the second time, we get y is equal to minus gt square by 2 plus u sine theta t. This is our equation of motion in terms of y, right, for the y direction. So we had x is equal to u cos theta t. So I'm just going to write it down over here. X is equal to u cos theta t. Now from here I can substitute for t. I can write t is equal to x by u cos theta and substitute this in this equation. We're gonna get y is equal to u sine theta, x by u cos theta, and minus half g x by u cos theta whole square, right? So this is just going to be u sine theta by u cos theta, and of course x, minus 1 by 2 gx square by u cos square theta. Now sin theta by cos theta is just tan theta, and u gets cancelled out. So it is going to be tan theta, x tan theta minus 1 by 2, sorry, x, that is going to be minus gx square by 2u cos square theta, right? This is the equation of trajectory that we obtain. This is known as equation of trajectory. Now this equation may not look very familiar at first, but notice that tan theta, tan theta and g by 2 u cos square theta all are constants, right? So I can substitute tan theta is equal to a and g by 2 u square cos square theta, sorry, 2 u cos square theta to be equal to v. So upon doing that, this equation actually transforms into y equals to ax minus bx square. Now this equation looks very familiar. This is actually the equation of a parabola, but to just to get the confirmation, if we put x is equal to 0, then in this equation, then we see that y is equal to 0. So the graph passes through the origin is very clear. If we put y is equal to 0, then we see that ax is equal to bx square, or x is equal to a by b. This is the x-intercept where the graph cuts the x-axis, and taking the derivative of this equation ax minus bx square, the first derivative is going to be a minus 2bx. The second derivative is going to be minus 2b, which is less than 0. So the graph is concave down, right? So now we can just draw the graph. This is the x-axis and this is the y-axis. So it starts at the origin and it is concave down, and it cuts the x-axis at a point, say a by b. So, and the object was projected somewhat like this, making angle theta. So clearly this is the graph of a parabola, right? This is the graph of a parabola. So finally, we have actually come to the conclusion of our problem statement that if a projectile if an object was undergoing projectile motion and we had no idea of the experimental results, still we can actually calculate what trajectory or what path that particle is going to follow under certain given boundary conditions, right? So it comes out to be a parabola.